In this class, I would like to explain applications of radiation force. The first application is, before going to explain first application, let me remind the required formulae for this applications. For example, if it is the perfect absorbing surface, if the radiation of intensity is I is made to incident slantly, this is the radiation of intensity I made to incident on perfect absorber. This is the perfect absorber. So angle made by incident radiation with this normal of the plane of absorbing surface is theta. Then the force exerted by this light is absorbed and it can exert force in the direction of that incident radiation, and it is equal to Ia cos theta by C. That is the formula already we derived. Force exerted by the radiation when it get absorbed by the surface completely. Theta is angle between this normal to the plane and direction of incident radiation. Clear? Now if it is a perfect reflecting surface, the same radiation of intensity is I, making theta angle with this normal. It is the perfect reflecting surface, reflector. Now the direction of force due to this radiation always perpendicular to plane of the reflector, not in this direction. So this is the force. Direction of force always perpendicular to the plane of the reflector. You should remember, already I explained those, right? Based on the transfer of momentum, we will get the direction of force. Now the direction of force always perpendicular to plane of the reflector. It is independent of the direction of the angle made by incident radiation. If you incident the radiation on the surface in any manner, the force due to that radiation always perpendicular to its plane in this direction. But here during absorption, it is always in the direction of the incident radiation. This force is in the direction of incident radiation. That is the difference. Now here we have derived 2Ia cos square theta by C. This is the formula. Remember those two formulae. I am going to use these two here. You can see first application. In this we have an object of mass m, which is a perfect absorber. Absorption coefficient is 1, which is suspended with the help of this uniform massless string, and radiation is incident on this surface perpendicular to its surface to keep this object at equilibrium at this position where that string is making theta angle with this vertical. Because of the radiation force on this absorbing material, so it is kept at this position with an angle theta with the vertical position. Now you can see here, because of absorption, the force, direction of force on this material is in the direction of this incident radiation, that is equal to Ia, based on this formula, Ia cos theta by C. What is theta? Angle between this normal and direction of radiation. It is either 180 or 0. We take the magnitude only. So cos this value is 1, Ia by C. This angle between these two. This is the normal incidence perpendicular to plane of this object. Now because of this force, it is in equilibrium state. So under how many force this body is in equilibrium state? This string force tension and radiation force F and gravitational force mg. Clear? These are the three forces acting on this object. Gravitational force mg. If I extend this line, this is theta. Now component of this mg in this direction, mg cos theta, and in this direction mg sin theta. You can see here in this direction there is no net force on this object. At steady state these two are equal, these two are equal. So you can write directly here T is equal to mg cos theta relation 1, F is equal to mg sin theta. Now F is what? IA by C mg sin theta. So mass of this material is, mass of this body is IA by C g sin theta. This is the equation. Or you can also write sin theta equal to IA by mg into C. This is the first case. Now in the same case, if it is the perfect reflector, if it is the reflector, perfect reflector means R equal to 1, a reflection coefficient. Now here normal incidence, so based on this formula again theta 0 or 180, then you will have 2IA by C for perfect reflector. The direction of force on reflector always perpendicular to its plane, means in the same direction of that force on absorbing material, but magnitude is 2 times of that, 2IA by C. Now here you will have 2, except this the remaining is same. So here the mass of this reflecting body is 2IA by Cg sin theta. Clear? This is the perfect reflector. Mass of the perfect reflector is 2IA by Cg sin theta. Now second application, the same absorbing object, mass m, suspended like this. Now the radiation is allowed to incident like this. It is always along the direction of this horizontal, along horizontal direction. This is not a normal incident on this surface of this absorbing material. Here this radiation is striking slantly. Angle between this normal and direction of incident radiation is, so if it is theta, this is 90 minus theta, this is theta. So this intensity of radiation is I, angle between this direction of incident radiation and normal of this plane is theta. So but this is the absorbing material, the force on absorbing material, force on absorbing material always in the direction of incident radiation, means along this horizontal. So what is that force? I based on this, IA theta angle between the normal and the direction of incident radiation, theta cos theta by C, that is F. Now weight of this body is vertically downwards. Now in this direction extend this, if it is theta, this is also theta. Now component of the tension in this direction T cos theta, in this direction T sin theta. You can see at equilibrium state these two are equal and these two are equal. So T sin theta is equal to F equation 1 and T cos theta is equal to mg equation number 2. If I divide those two equations, if I divide equation 1 with equation 2, equation 1 divided by equation 2 implies tan theta is equal to F by mg. So F equal to mg tan theta. But what is F? Already we have written here, IA cos theta by C equal to mg tan theta. So therefore from this mass of this object absorber is IA cos theta. You can write this as sin theta by cos theta. It becomes cos square theta by g c sin theta. This is the mass of this absorbing body when radiation strikes along horizontally, and it is kept in equilibrium state at this position at which this string makes theta angle with vertical. Clear? Now, if the same material is a perfect reflector, if I assume the same object is perfect reflector, if it is the reflector or equal to 1, then the same radiation will exert the force, but the force is not along the direction of this incident. On reflecting body, force is always perpendicular to this surface of the object, perpendicular to the plane of this material. So like this is the force, right? The force is acting like this, but that force is what? For reflector, this one, 2ia cos square theta by c. That is the force. And here you can see carefully. Here again you can resolve the mg into components. So in this direction mg cos theta, and in this direction along this normal, along the normal mg sin theta. So you can see here at equilibrium state T is equal to mg cos theta and F equal to mg sin theta. F equal to mg sin theta. Relation 1, relation number 2. From those two relations, for mass of this material, mass of this object is now from force F equal to mg into sin theta. F is what? 2ia cos square theta by c equal to mg into sin theta. So mass of this object suspended with this string is 2ia cos square theta by g into c sin theta. Very easier. So try to learn how to write the